So hello everyone, welcome you all to this new video. So in our previous videos we have solved many problems related to work done, work done by a surface line integral, simple line integral. According to the application of work line integral, we have seen the formula for work done as integration of f dot dr, that is work done by a force with respect to the movement in the position of the vector. So we have seen that relation and we have solved many problems related to that, and those who have not seen those videos, please go and watch it. Detailed explanation is given in those videos. So in this video we are just going to continue with the second chapter, that is Green's theorem. This is one more important theorem of this chapter, Green's theorem, very important one. So let us see what is this Green's theorem, and let us get to one conclusion what formula we would be getting from this Green's theorem. Green's theorem means if R could be any region, is a closed region. If R represents a closed region in the xy plane, they mentioned it as the xy plane, so listen carefully. If R is a closed region in the xy plane bounded by the simple closed curve C, and m of x comma y and n of x comma y are continuous functions. The m is a continuous function which consists of variables x and y, so as n are continuous functions having the partial derivatives in R, that is in the closed region it has its partial derivatives. Then the relationship between this whole thing of Green's theorem is given by integration over a closed surface m dx plus n dy, where m and n are the continuous functions. It is equal to double integration of R, double integration of R dou n by dou x minus dou m by dou y into dx dy. So this is the relationship between the closed region in the xy plane and the continuous functions m and n. That is integral of closed surface, line integral over a closed region, m dx plus n dy is equal to double integral or surface integral, we could be calling it, double integral of the region dou n by that is the partial derivative dou by dou x into n minus dou by dou y into m into dx dy. So this is the simple relationship for the Green's theorem. So now related to this formula for Green's theorem, we are going to solve many problems now, very important problems. They would be giving you some conditions. So related to that condition, we should be plotting the graphs now. We should be drawing the graphs related to that condition. That plays a very important role. So yeah, let us see with some of the problems of Green's theorem, and let us see what different variations we get during solving the problems. So here is the first question. First question: use Green's theorem to evaluate the particular integral mentioned here, that is integral over a closed surface xy plus y square dx plus x square dy, where C is the closed surface curve made up of line y is equal to x and parabola y is equal to x square. So this is the question here. I have told you should be plotting graph, right, with the given conditions y equal to x and y equal to x square. So here if you observe carefully this term here, the general equation of Green's theorem is what? M dx plus n dy, right? That is equal to double integral over a region dou n by dou x minus dou m by dou y dx dy, right? So this is the formula for Green's theorem, right? So here they have given the left hand side the part where this term is equal to the, in place of xy plus y square we can write it as m, in place of x square we can write it as n. Yeah, so we'll solve that. How to solve, let us see. Before that, plot the graph from the given conditions y equal to x and y equal to x square. Let us see how to plot it now. First, this plot is very important for the integration limits. In order to calculate, in order to see what are the limits of x and y, these things play a vital role. That is how I'm going to tell you. First, let us draw a parabola y equal to x square. Since parabola is drawn like this, you know that this is y-axis, x-axis. For all the values of x here, these are the values of x. The y value would be equal, that is x square. So 0 square is 0, 1 square is 1. If the value of x is 1, so 1 square is 1, also minus 1 square is 1, so y would be equal. Okay, so like that we would be getting the conclusion that like this the parabola would be looking y equal to x square. Also they are mentioned to draw x is equal to y line, that is this part, slope part. This is the line of x equal to y. So this is from the origin. You should be drawing one line perpendicularly, straight line, so that the value of x would be equal to y. That is 0 0. Here 1 1, 2 2, 3 3, 4 4, so on. Okay, the values of x and y are equal. Okay, this is at 0 0. If x is 1 here, y also should be 1. So this would be intersecting here. If x is 2, y is also 2. It would be intersecting here, and we would be forming one slope. Okay, so this is the line of x equal to y. They have given the two conditions, y equal to x and y equal to x square. For that we have drawn the lines. Now where the two lines curves, right, are intersecting, right, that region you should be shading here. Okay, why? Because from that region you are going to check out the limits here. Okay, so I am just going to extend this parabolic curve here. Okay, so that I could shade well. Yeah. Okay, wherever it is intersecting, the point of intersection you should be checking for the limits. That I am going to tell you now. That is to find the limits of y. Okay, for which term is common, right, in the given condition, in the given question, that you should be checking the limits in the graph. And the other term, that is x and x square, you should be solving manually and checking. Okay, to find the limits of y from x tending to y. Okay, wherever the curve is meeting at x, right, from that point, wherever the curve is meeting at y, we should be drawing one perpendicular, so that the limits would be from this starting point x here. In x axis it is touching here, the curve here is of x square, to ending point is this, that is the curve here is x. Okay, so the limits of y are from x square to x. Okay, now let us check the limits of x here now. For that you should be solving manually using Green's theorem. Okay, hope it is clear. So now by Green's theorem, solve it now by GT stands for Green's theorem. So while solving the problems, this is the abbreviation I am going to use in all the problems. So GT stands for Green's theorem. We know that m dx plus n dy, right? Here in the given question, m is equal to xy plus y square and n is equal to x square, right? So now in the right hand side we have one term dou m by dou y. Okay, so let us solve that. That is, we should partially differentiating this term with respect to y. So in these two terms, both the sides we have y. So differentiation of y is 1. Here we have only x now, plus differentiation of y square is 2y. Similarly, in the other side we have dou n minus dou n by dou x. That is, dou by dou x is n, that is 2x. Now in order to find the limits of x here we have y equal to x and y equal to x square, right? So how we can find? You can see that x is equal to x square from these two conditions, right? So we got one rule here. So what we could be doing, x minus x square equal to 0, or x into x minus 1, just have taken x common. Okay, so we would be getting this term that is equal to 0. So we would be getting x equal to 0 and x minus 1 equal to 0. So x equal to 0 and x equal to 1. So you can say that x tends from 0 to 1. Okay, so hope it is clear. So the limits are, I am writing it here again, limits. These limits play a vital role. For x, limit is from 0 to 1, and for y, from the graph, the limit is from x square to x. Okay, so hope it is clear. Now let us do the integration part, that is this part, integration of m dx plus n dy, that is integration of m dx plus n dy. Is equal to double integration of dou m minus dou y, sorry, this term dou n minus dou x minus dou m by dou y into dx dy, right? So this is the formula. According to here the question, the limits are from, so here we have dx dy, so first we have dx, so in the first integral write the limits of x, that is from 0 to 1. The second are from limits of y, x square to x. Okay, dou n minus dou x, dou n minus dou x is 2x minus dou m by dou y is x plus 2y, so 2x minus x plus 2y, 2x minus x is plus x, so we are left with x plus 2y dy dx dy. Okay, so step by step let us solve it now. I'll do it in the next page. That is x square to x 0 to 1 x minus 2y dx dy. Okay, so you hope you know to solve the double integrations and all. First do the inner part, that is x square to x, keep it as it is. Take the integration of this part, that is x minus 2y with respect to dx, so x dx is x dy is xy minus 2 into y. The integration of y is y square by 2, so 2 will be getting cancelled, you will be left with only y square. Okay, and now the limits are from I made a mistake, sorry, let us solve it again. X square to x dx, that is x square by 2, and 2y dx, that is dx, that is 2xy. 0 to 1 limits dy. So x square, so do the upper limit minus lower limit, that is 1 by 2 minus 2y minus 1 by 2 minus 0 dy. So x square to x 1 by 2 minus 2y minus 1 by 2 dy. So 1 by 2 goes, we are left with 2y dy. Okay, now minus 2 take it common, x square to x y dy, so that is minus 2 into y square by 2 x square and x, upper limit, that is x square minus x square, and in place of y is x square, so x to the power 4 divided by 2, so 2 gets cancelled, so we are left with x to the power 4 minus plus, so x to the power 4 minus x square. Okay, so this is the required answer. So hope it is clear. So let us solve one more problem.